Hello, and welcome to Physics Before Bed. If you're ready to unwind with some thought-provoking science, you're in the right place. Before we dive into tonight's exploration, make sure to like this video and subscribe to stay up to date with all our latest content. And hey, drop a comment below and let us know where you're watching or listening from. Is it morning where you are, or perhaps a late night wind down? Wherever you're tuning in from, tonight's topic is a journey through time itself. We'll be delving into one of the most fundamental questions in physics and philosophy. Why does time only move forward? As we explore the arrow of time, think about it this way. Whether you're in the past, present, or future, time marches on in only one direction. But why? What makes the clock tick in that unyielding forward motion? Is it an immutable law of the universe, or are there hidden complexities lurking beneath the surface? Let's find out together. Grab a cup of tea, settle in, and let's begin. Time. It's something we all experience, yet something we don't often think about. We wake up, move through our day, and fall asleep, all within the unyielding flow of time. But here's the intriguing question. Why does time only seem to move forward? The idea of time flowing in one direction is so familiar to us that we rarely pause to consider why that is. After all, in our daily lives, time appears to move like an arrow. Once it's gone, it's gone. But what if this constant forward motion isn't as simple as it seems? What if time could be something entirely different? For centuries, thinkers and scientists have pondered the directionality of time, and the answers they've come up with have shaped how we view everything from the cosmos to our personal experiences. In ancient civilizations, the concept of time was often cyclical. Many cultures, such as the ancient Egyptians, viewed time as a series of repeating cycles, the sun rising and setting, the seasons changing. Everything had a natural rhythm that went on endlessly. For the Egyptians, time was like a wheel, turning forever in a loop. Similarly, in Eastern philosophies, like Hinduism and Buddhism, time was often seen as a never-ending cycle of birth, death, and rebirth. Time didn't move in one direction, but rather spiraled endlessly, creating a sense of eternity. It wasn't until Western thinkers began exploring the nature of time that this view began to change. In the 17th century, Isaac Newton, one of the most influential scientists in history, proposed that time was an absolute, unchanging force that flowed uniformly throughout the universe. In his view, time didn't care about events happening within it. It simply passed, ticking forward at a constant rate. This vision of time as a mechanical and uniform progression, regardless of what was happening around it, became the dominant perspective in the world of science. But as time went on, a number of scientists and philosophers started to notice that something felt a bit off about this rigid, one-size-fits-all view of time. Henri Bergson, a French philosopher in the late 19th and early 20th centuries, offered a very different perspective. He argued that time, or at least our experience of it, is far more fluid than Newton's mechanical clockwork. For Bergson, time wasn't something that could simply be measured in units, like hours or minutes. Instead, he believed time is subjective, deeply connected to the rhythms of life itself. He called this la durée, or duration, which refers to the lived experience of time, how it feels to move through it, how it stretches and contracts depending on what's happening in our lives. Bergson's ideas were revolutionary. Instead of time being a fixed mechanical force, it was something much more personal and malleable. This view contrasted sharply with Newton's idea of time as an unbending ruler, measuring everything with the same precision. Bergson proposed that our experience of time could vary, influenced by the mental and emotional states we are in. Think about a moment when you're waiting for something. Time seems to drag on. But when you're doing something enjoyable, time can feel like it's flying by. For Bergson, that sensation wasn't just a trick of the mind. It was the true nature of time itself. Time, for him, was more like a flowing river than a ticking clock. But if time is so fluid and subjective, how do we explain the undeniable fact that it appears to move in one direction? The idea of time's arrow, the way time flows inexorably forward and never backward, has puzzled many, and its implications go far beyond philosophy. This notion of time's arrow was first really solidified in the 19th century by the work of scientists exploring the second law of thermodynamics. The second law tells us that in any closed system, disorder or entropy will always increase. This means that things naturally progress from states of order to disorder. Think about a hot cup of coffee sitting in a cold room. The heat from the coffee will spread into the room, gradually cooling the coffee and warming the air. Eventually, the coffee and the room will reach the same temperature, and the heat will be evenly distributed. In this process, the disorder, the spread of energy, has increased. What's important here is that this process only goes one way. Once the coffee cools down, it won't spontaneously heat up again. The arrow of time, in this sense, is tied directly to the increase in entropy. The rise of disorder is irreversible, and in the world of physics, that irreversibility is what gives time its forward flow. However, this brings us to a very interesting point. If time is really driven by entropy, then why does it always move forward rather than backward? Could we, in theory, reverse entropy and make time flow backward? These are some of the questions that have intrigued scientists for years, but before we jump into those deeper mysteries, it's important to consider the strange and subtle relationship between time's flow and the laws of nature. And that brings us to the more modern theories that have attempted to shed light on why time has this unrelenting forward progression. Some physicists, like the late British scientist Stephen Hawking, proposed that the arrow of time might be connected to the overall expansion of the universe. According to Hawking's theory, when the universe began with the Big Bang, it was a highly ordered state. Everything was packed into a tiny point of infinite density. As the universe expanded and cooled, entropy began to rise, and the direction of time was set. From that moment on, the universe has been getting more disordered, and thus time has moved forward ever since. Hawking also suggested that the entire universe has an arrow of time, one that aligns with the increasing entropy of the universe. But not all explanations of time's arrow are tied to entropy. As we've seen, time can also be subjective, something that feels different based on our personal experiences. And then there's the more abstract notion of time found in quantum mechanics. In quantum theory, time behaves in strange ways. Particles don't have definite positions until they're observed, and their behavior doesn't follow the same rules as the classical world. This has led some researchers to propose that time itself may not be a fundamental feature of the universe, but rather an emergent property that arises from more fundamental quantum processes. In this view, time isn't a constant. Instead, it could arise from the relationships between quantum particles, which could make the flow of time more flexible than we've imagined. For now, we may not have a concrete answer to why time only seems to move forward, but the pursuit of this question has been one of the most exciting and mind-bending aspects of modern physics. From Bergson's fluid, subjective time to the scientific exploration of entropy, cosmology, and quantum mechanics, time's arrow continues to be a fascinating mystery. And in the next chapters, we'll dive deeper into the scientific theories that shape our understanding of time, exploring some unconventional viewpoints along the way. So stay with us as we unravel the enigma of time's directionality. It's going to be quite the journey. What is time? It's one of those questions that seems deceptively simple, yet the more we try to define it, the deeper we find ourselves drawn into a web of complexities. Time governs everything from the way we experience the world to the very fabric of the universe. But is it really what we think it is? Is time a constant force, something that moves forward regardless of our experience? Or is it something more abstract, a concept shaped by our minds and our place in the universe? Let's explore time from a few different perspectives, philosophical, psychological and physical, and see how each lens offers a different answer to this fascinating question. Philosophers have spent centuries debating the true nature of time. Is it a fundamental aspect of reality, existing independently of human consciousness? Or is it simply a mental construct, a product of our perception? In the early days of philosophy, time was often treated as a sort of metaphysical constant. The ancient Greeks, for instance, viewed time as something eternal, something that existed independently of the individual. It was Plato who famously described time as the moving image of eternity, something that mirrors the unchanging nature of the cosmos. But as philosophy evolved, so did our understanding of time. By the 19th and 20th centuries, thinkers began to challenge the idea that time was an objective feature of the universe. One of the most influential thinkers in this shift was the French philosopher Henri Bergson. He proposed that time, or at least our experience of time, is much more fluid than we tend to think. For Bergson, time wasn't something that could be measured with a clock. Instead, It was something that lived in our experiences, what he called la durée, or duration. According to Bergson, the true nature of time is subjective, stretching and compressing depending on our emotional and mental states. For instance, when we're engaged in something enjoyable, time seems to fly. When we're bored or waiting for something, it seems to drag on. Time, in Bergson's view, isn't a mechanical force, it's a personal, lived experience. Then there's the perspective of British philosopher Michael Lockwood, who explored time's relational nature. Rather than thinking of time as a linear, independent force, Lockwood argued that time is inextricably tied to events and experiences. In his view, time doesn't exist in a vacuum, it is always experienced in relation to something. Without events to happen, time itself would be meaningless. Lockwood's ideas suggest that our understanding of time is more closely linked to the events we experience than to a fixed, objective clock that ticks away in the background. This notion leads us to another intriguing question. Does time even exist independently of us? This is a question that takes us into the heart of metaphysics, a branch of philosophy concerned with the fundamental nature of reality. For Immanuel Kant, one of the most influential philosophers of the 18th century, time wasn't an external force that existed independently of the observer. Instead, Kant argued that time, along with space, was something we impose on the world. In other words, time is a lens through which we experience reality. According to Kant, the structure of time is hardwired into our minds. It's not something we observe in the external world. Time is a feature of how we perceive the world, not necessarily how it actually is. On a more practical level, many of us think about time in terms of seconds, minutes, and hours, units of measurement we use to organize our daily lives. But these units, like the clocks and calendars we rely on, are deeply connected to human culture and technology. The way we measure time is not universal. It's a construct that has evolved over centuries. Ancient civilizations measured time by the movement of the stars and the sun, tracking the phases of the moon and the changing of the seasons. The ancient Egyptians, for example, developed one of the earliest known calendars based on the lunar cycle. It was only with the development of mechanical clocks in the Middle Ages that we began to think of time as something that could be measured with precision, down to the second. This technological evolution has continued, with the development of atomic clocks, devices that measure time based on the vibrations of atoms, specifically cesium atoms. An atomic clock is so precise that it will only lose 1 second every 100 million years. The technology we use to measure time has come a long way from the ancient sundial or water clock, and it reflects how our understanding of time has deepened and become more sophisticated. Yet despite these advances, the way we experience time on a personal level remains subjective and often tied to our biology. This brings us to the fascinating intersection of time and human biology. Our experience of time is closely connected to the biological rhythms of our bodies. Our circadian rhythms, which govern our sleep-wake cycle, are an example of how time is woven into our very existence. These internal clocks help regulate everything from hormone production to metabolism. The fact that we have these internal biological markers of time suggests that our experience of time isn't just an abstract concept. It's something rooted in our biology and the rhythms of life itself. And yet, despite the advances in our understanding of time and the technology we use to measure it, we still don't fully understand what time is. Is it an illusion, a mental construct, or is it a fundamental feature of the universe, one that governs everything from the smallest particles to the largest galaxies? In the world of physics, time is often treated as a fourth dimension, a dimension intertwined with space to form the very fabric of the universe itself, what we call space-time. This idea was revolutionized by Albert Einstein's theory of relativity, which showed that time isn't as constant as it seems. According to relativity, time can be warped by gravity, and it can move at different rates depending on how fast you're moving or how close you are to a massive object like a planet or star. This bending of time, known as time dilation, has been proven through experiments with atomic clocks, flown on planes, or placed in satellites. Relativity tells us that time is not a fixed universal measure. It's malleable, tied to the very structure of space itself. This idea, which has become central to modern physics, suggests that time is far more dynamic and complex than our everyday experiences would lead us to believe. But despite all the breakthroughs, the true nature of time remains elusive. Is it simply a construct of our minds, shaped by our perceptions and experiences? Or is it a deeper feature of the universe, one that we have yet to fully comprehend? As we continue to explore the mysteries of time, we are constantly confronted with new questions that blur the line between philosophy and science, between the subjective experience of time and the objective reality of the universe. Time, it seems, is not a single, easy-to-define concept. It is an enigma, one that continues to fascinate and puzzle us. Whether we're measuring it with the most precise atomic clocks or feeling it stretch and contract in the depths of our consciousness, time remains one of the greatest mysteries of our existence. One of the most fundamental concepts in the universe is the second law of thermodynamics, a principle that governs the flow of energy and entropy, and in turn plays a significant role in our understanding of time itself. The second law tells us that in any closed system, entropy, essentially a measure of disorder, will always increase. This law is often described as the reason why time moves forward. As entropy rises, so too does the progression of time, making it one of the most direct ways we experience the arrow of time. At its core, the second law of thermodynamics asserts that systems naturally evolve from states of order to states of disorder. Imagine a room full of gas particles in perfect order, all moving in a highly coordinated way. Over time, those particles will move randomly, increasing the disorder or entropy of the system. This increasing entropy is irreversible, and that's where the connection to time comes in. The second law, and its inevitable increase in entropy, suggests a directionality to time. This is why we perceive time moving only in one direction, from order to disorder. But how does this apply to the universe at large? How does it influence time on a cosmic scale? Let's start with the work of David Z. Albert, a philosopher and physicist who explored how the second law of thermodynamics fits into our broader understanding of space-time. Albert's most controversial view involves the idea of the block universe, a concept that has intrigued physicists and philosophers alike. The block universe model suggests that past, present, and future all exist simultaneously, like a massive block of time where all events are already laid out. In this view, time isn't flowing. Instead, it's already set, and we merely perceive it as moving because of our limited perspective. Albert ties this model to the laws of thermodynamics, suggesting that the increase in entropy is what gives us the sense of time flowing. In his framework, entropy's inevitable rise ensures that time progresses in a single direction, even though in the block universe all moments already exist. Albert's idea is certainly provocative, and it challenges the traditional view of time as something that flows, passing from one moment to the next. If the block universe is correct, time, in the conventional sense, is an illusion. This has profound implications for how we experience time. We might feel like we're moving through time, but in a block universe, it's as though we are simply observing a grand, immutable structure, one that is already written. But time's relationship with entropy doesn't just apply to the cosmos or large-scale systems, it extends to biological systems as well. In his work, What is Life?, the physicist and biologist Erwin Schrödinger explored how thermodynamics could explain the behavior of living organisms. Schrödinger argued that living systems appear to defy the natural tendency toward increased disorder, or entropy. They seem to maintain order within themselves, growing, repairing, and reproducing, which suggests they are managing entropy in some way. Schrödinger proposed that living organisms extract negative entropy from outside their system, in order to maintain their structure. This concept was revolutionary, as it extended the laws of thermodynamics to life itself, showing that biological systems play an active role in managing the flow of entropy. This idea is essential to our understanding of time because it suggests that living systems don't just passively experience the flow of entropy. Instead, they act to maintain a state of low entropy within their boundaries. This continuous management of entropy is a key aspect of the biological arrow of time. The processes of life, from cellular metabolism to aging, all involve intricate balancing acts that deal with entropy in ways that non-living systems do not. However, the story of time and entropy doesn't end with Schrödinger's insights. There are other physicists who have gone further, proposing more radical ideas about the relationship between time, thermodynamics, and the nature of the universe. One such thinker is Roger Penrose, a British physicist known for his work on black holes and cosmology. Penrose introduced the idea of thermodynamic time asymmetry, which challenges the conventional view of time's flow in quantum systems. According to Penrose, the arrow of time is not always tied to entropy's increase. In certain situations, particularly near black holes, time behaves in unusual and unexpected ways. Penrose's theories, particularly his work on the thermodynamics of black holes, suggest that the structure of space-time itself could influence the way time moves. In the vicinity of black holes, time appears to slow down as one approaches the event horizon, the boundary beyond which nothing, not even light, can escape. This phenomenon, known as time dilation, has been experimentally verified using atomic clocks, which show that time moves more slowly in stronger gravitational fields. Penrose took this idea further by exploring how the universe might have started in a state of low entropy and evolved into a more disordered, thermodynamically rich state. In this view, time is deeply intertwined with the fabric of space-time, and its directionality is shaped by more than just entropy. Penrose's work has sparked debates and opened the door for alternative models of time, particularly in relation to the quantum world. Traditional quantum mechanics in many ways treats time as something reversible, where the equations governing particles can move forward or backward with no difference. But when you bring thermodynamics into the picture, things change. Penrose's theory suggests that, on a cosmic scale, time's flow may not be as symmetrical as quantum mechanics implies. There's a deeper connection between time, entropy, and the fabric of the universe that we still don't fully understand. Yet there are still physicists who challenge the assumption that time must always move in one direction. Lee Smolin, a theoretical physicist, has proposed an intriguing idea that challenges the very notion of time as we know it. Smolin's hypothesis is that time may be fundamentally discrete. In other words, time might not be continuous as we experience it, but instead could be made up of individual time slices. This idea flips the traditional model of time as a smooth, uninterrupted flow, suggesting instead that time could evolve, with each slice of time representing a discrete moment. Smolin also explores the idea that time itself might be the key to understanding the evolution of the universe. His theory proposes that space-time, rather than being static or fixed, could evolve with time, much like living organisms grow and change. According to Smolin, the laws of physics, including the second law of thermodynamics, could be evolving over time. In this model, the universe doesn't follow a predetermined path. Instead, it's a dynamic, evolving system, with time playing a crucial role in shaping its future. Smolin's work provides an alternative view to the block universe, where time is not an illusion, but a central, evolving feature of reality. His theory suggests that the universe is not a fixed entity, but one that is continuously being created and recreated, with time at the heart of its ongoing transformation. So, as we consider these various perspectives on time, from the block universe to the evolving space-time of Smolin's theories, we see that time is far from being a simple, straightforward concept. Whether it's the increasing entropy of thermodynamics, the deep time implications of black holes, or the dynamic evolution of space-time, time remains one of the most elusive and fascinating aspects of our universe. What is time? Is it a constant flowing forward only because of entropy? Is it an illusion, an aspect of our minds? Or is it something far more complex, evolving and changing in ways we're only beginning to understand? As we continue to explore these questions, one thing is clear. The nature of time is deeply intertwined with the most fundamental processes of the universe. From the simplest systems to the grandest cosmic phenomena, time shapes everything. And as our understanding of time deepens, we may find ourselves unraveling some of the greatest mysteries of existence itself. Entropy. It's a concept that's become synonymous with disorder, chaos, and the inevitable breakdown of systems. According to the second law of thermodynamics, in a closed system, entropy will always increase over time. The universe, in its constant progression, moves toward greater disorder. But this idea, while fascinating, is not the full story. The relationship between entropy and the flow of time is far more nuanced than a simple move from order to disorder. Ilya Prigogine, a Belgian physicist and chemist, introduced an idea that challenged this view, suggesting that time might have a more organic dynamic quality than we traditionally thought. In his work on dissipative structures and non-equilibrium thermodynamics, Prigogine explored how systems far from equilibrium, those not in a state of perfect balance, could evolve and give rise to complex ordered structures. The surprising twist here is that the rise of disorder, the increase in entropy, doesn't necessarily lead to a uniform state of chaos. In some cases, it can lead to order, structure, and even life itself. Prigoghine's theory, which earned him the Nobel Prize in Chemistry in 1977, suggested that entropy doesn't always lead to complete disorder. Instead, under the right conditions, it can trigger self-organization, where systems spontaneously develop complex structures without any central command. This idea revolutionized our understanding of how time and entropy interact. It challenges the classical view that the increase in entropy must always result in decay and disorder. Instead, it opens up the possibility that time, and the movement toward greater entropy, could lead to new forms of order, complexity, and even life. Take, for instance, the formation of snowflakes. When water freezes, the molecules arrange themselves in a highly ordered crystalline structure. This is a result of the system moving toward a lower energy state, but it's a process that creates something with more order, not less. Similarly, the development of life is another example of how entropy's increase can lead to a higher level of organization. The very biological processes that allow life to exist, from the formation of complex molecules like DNA to the self-repair mechanisms in our cells, are rooted in entropy. But instead of just collapsing into disorder, life harnesses entropy, using it to create structure and complexity. This phenomenon challenges the classical notion that time moves inevitably in one direction toward greater disorder. If we think of time as a relentless march toward chaos, then how do we explain the fact that in certain circumstances, complexity emerges from what seems to be disorder? In a sense, time doesn't just move forward toward more randomness, it also paves the way for the creation of new structures. It's a reminder that entropy, while it increases, can also create the conditions for greater and more sophisticated levels of organization. One way to think about this is through the concept of negentropy, or negative entropy. This is the idea that certain systems, particularly living systems, maintain or even increase their order by exchanging energy with their surroundings. For example, when we eat food, we're taking in energy that allows our bodies to maintain a high level of internal order. In doing so, we fight against the natural progression toward disorder. The second law of thermodynamics tells us that the total entropy of a closed system will increase over time. But living organisms are not closed systems. We import energy, maintain our structure, and export entropy into our environment. The Chilean biologist Francisco Varela explored this concept in depth. He proposed that living organisms actively maintain their internal order by constantly exchanging energy with their surroundings, effectively fighting entropy in a delicate balancing act. In Varela's view, life is an ongoing process of creating and maintaining order against the tide of increasing entropy. This idea not only adds a layer of complexity to our understanding of time and entropy, but also suggests that life itself is intricately linked to the flow of time. Time, in this sense, isn't just about the passive unfolding of events. It's about actively managing the passage of time to maintain order and life. But if we step back from biological systems for a moment and think about the universe as a whole, we encounter another challenge to the conventional understanding of time's arrow. The second law of thermodynamics, which dictates that entropy must increase in a closed system, forms the basis for much of our thinking about the directionality of time. But this law also has an interesting implication. It tells us that the universe is constantly heading toward greater disorder, a state that some scientists refer to as the heat death of the universe. In this scenario, the universe will eventually reach a state where all the energy is evenly spread out and there is no more work that can be done. This is often presented as the ultimate endpoint of time, an eternal, unchanging state of maximum entropy. However, not all theories about time and entropy lead us to this ultimate conclusion. Physicists like Roger Penrose have proposed an alternative view, one that adds another layer of complexity to the idea of time's arrow. Penrose's theory of thermodynamic time asymmetry challenges the conventional wisdom of time moving in one direction toward disorder. Penrose suggests that the flow of time could behave differently under extreme conditions, such as near black holes or at the quantum level. His work on black holes and cosmology has led him to propose that time, in some contexts, may not behave the way we traditionally think it does. In particular, Penrose introduced the idea that time's arrow might not be as straightforward as we've imagined. When we look at the behavior of black holes, for example, time appears to behave differently than it does in more familiar environments. The intense gravity near a black hole warps the fabric of space-time, slowing time down for an observer in that region compared to one far away. This dilation of time is not just a theoretical curiosity. It has real implications for how we think about the nature of time and its relationship to the physical world. Time, in this view, becomes intertwined with the structure of space itself. Penrose's ideas about the asymmetry of time, how time might not always flow in one direction, especially in the extreme environments of black holes, suggest that time is more flexible and more complex than we have thought. His work invites us to rethink the very nature of time's forward motion, suggesting that, under certain conditions, time's directionality might not be set in stone. Meanwhile, physicists like Lee Smolin have gone even further in challenging our conventional understanding of time. Smolin proposes that time might not be continuous at all, but rather discrete, made up of individual time slices that evolve from one moment to the next. This model stands in stark contrast to the smooth, continuous flow of time that we typically imagine. Instead of time flowing like a river, Smolin suggests it might evolve in a more granular step-by-step manner. In his view, time doesn't just march forward in an unbroken line. It evolves, and this evolution might be central to the way the universe works. Smolin also proposes that the laws of physics themselves could evolve over time, rather than being fixed. This theory, known as evolving laws, posits that the universe could change in ways that we don't yet fully understand. This evolving nature of the universe would mean that time isn't just a passive backdrop for events, but is actively shaping the way things unfold. At the intersection of these ideas, whether it's Penrose's thermodynamic asymmetry, Smolin's discrete time, or Prigoghine's self-organizing systems, one thing becomes clear: time is far more complex than we typically assume. It is not merely a forward march toward entropy and disorder. Instead, it is a dynamic, evolving phenomenon that interacts with the very fabric of reality in ways that are still unfolding. From the way life organizes itself to the behavior of black holes and the possibility of discrete time, the true nature of time remains one of the most profound mysteries of science. Whether we're looking at the universe as a whole, at the microscopic quantum world, or at the biological processes that sustain life, the interplay between entropy, time, and order reveals a deeper, more complex story. Time, it seems, is not just a one-way street. It's a constantly evolving force that continues to shape and be shaped by the universe around us. The universe is vast, and so too is our understanding of time within it. For centuries, we've tried to understand how time behaves across the cosmos, from the smallest particles to the grandest galaxies. And just like on Earth, time in the universe is thought to flow in one direction, moving from past to present to future. But when we zoom out and look at the universe as a whole, we begin to encounter theories that challenge our conventional understanding of time. One of the most fascinating modern ideas comes from Carlo Rovelli, an Italian theoretical physicist known for his work in the field of quantum gravity. Rovelli is one of the leading voices in a movement known as loop quantum gravity, which seeks to merge the principles of quantum mechanics with general relativity, the theory that describes gravity on a large scale. This is no easy feat, as these two pillars of modern physics are fundamentally incompatible in many ways, but Rovelli's work is pushing us closer to understanding how they might fit together, especially when it comes to time. In loop quantum gravity, time is treated quite differently from how we usually think of it. Rovelli and his colleagues propose that time, as we understand it, might not exist at the most fundamental level of the universe. Instead, time might be something that emerges from more basic quantum processes, just as space might emerge from even more fundamental quantum phenomena. This theory suggests that at the quantum level, where the laws of physics operate differently than at the scale of everyday life, time might not flow continuously. Instead, it might exist in discrete chunks, much like the way space is divided into small indivisible units in some quantum models. This challenges the classical view of time as an ever-flowing river, marching forward in a smooth and uninterrupted progression. In Rovelli's model, time is not a given, it's an emergent property of the physical universe. This view connects back to the theories of quantum mechanics, which often describe particles as being in multiple states at once, and time itself may behave in similarly strange and complex ways. Time, then, might not be an ever-present force, but something that arises when certain conditions are met, conditions that we may not yet fully understand. If we step back and think about how time operates on the larger scales, across galaxies, stars, and black holes, there are even more mind-bending theories to consider. One of these ideas comes from Julian Barbour, a British physicist whose work on the nature of time has challenged conventional wisdom. Barbour proposed that time, as we understand it, might be an illusion. In his view, the universe itself doesn't move through time the way we think. Instead, he suggests that what we experience as the passage of time is simply our perception of a series of events that are laid out in a timeless framework. These events, or snapshots, exist all at once, and our experience of time is just the perception of moving through these frozen moments. According to Barbour, if we could somehow view the universe from outside the flow of time, we would see not a continuous progression from past to future, but a collection of timeless events that are all equally real. This is a radical departure from the classical view of time. Barbour's theory suggests that time is not a fundamental feature of the universe, but rather a byproduct of how we experience events. In this model, time is more like a mental construct, rather than an intrinsic feature of the cosmos. Yet even as Barbour's theory has found supporters, it faces challenges, especially when we look at the origins of the universe. If time is an illusion, then what happens at the very beginning of the universe? Was there a starting point in time, or has time always existed? These questions have led cosmologists to explore models of the universe where time itself may have had a beginning, not just as a concept, but as something that emerged along with the cosmos itself. One such model comes from Alexander Vilenkin, a Russian-American cosmologist who has worked extensively on the origins of the universe and the nature of time. Vilenkin's work on the quantum creation of the universe suggests that time, as we know it, may have emerged from a quantum fluctuation, a spontaneous change in energy that leads to the creation of space-time. In this model, time doesn't exist in a traditional sense before the Big Bang. Instead, the universe, including time, began as a quantum fluctuation in a state of nothing. This view turns our understanding of time upside down. Instead of time stretching back infinitely, Vilenkin's model suggests that time itself had a beginning, tied to the very birth of the universe. The idea that time might not have existed before the Big Bang is both mind-boggling and fascinating. In this scenario, time isn't eternal. It's a property that emerged from quantum processes, fundamentally linking time to the evolution of the universe itself. Time, it seems, may be just as much a product of the cosmos as it is a measure of its unfolding. As we turn to the theory of relativity, the famous theory developed by Albert Einstein in the early 20th century, we see yet another layer added to our understanding of time. General relativity revolutionized our conception of space and time, showing that they are not separate entities but are intimately connected in what we call space-time. In relativity, time is not a constant independent flow. Instead, it is shaped by the presence of mass and energy. This leads to phenomena like time dilation, where time moves more slowly near massive objects like planets or black holes. The stronger the gravitational field, the slower time moves. This has been confirmed by experiments using atomic clocks, which show that time indeed runs slower in stronger gravitational fields. Einstein's theory also predicts that time is not the same everywhere in the universe. The fabric of space-time is curved by the presence of mass, and as a result, time behaves differently depending on where you are. If you were close to a black hole, for example, time would slow down dramatically. This is known as gravitational time dilation, and it's been confirmed by observing clocks placed at different altitudes on Earth. The clock at a higher altitude, farther from Earth's gravity, ticks slightly faster than one at sea level. This effect is incredibly small in our daily lives, but it becomes much more noticeable near large masses like black holes, or even in the early universe, when space-time itself was far more curved. Relativity also helps us understand the relationship between space and time in a broader sense. It tells us that time doesn't just flow independently of space, it's connected to the very structure of the universe. This connection between space and time means that events are always dependent on the observer's location and speed. What might seem like a single moment in time for one observed can appear stretched or contracted for another observer, moving at a different speed or near a different gravitational field. This idea challenges our usual experience of time as a universal, constant thing, and instead presents a view of time as something relative to the observer's position in space. Time, then, in the context of cosmology, is not a simple, linear progression. From quantum fluctuations that give rise to the universe itself, to the way space-time is shaped by mass and energy, to the possibility that time might not even exist at the most fundamental level, our understanding of time is continually evolving. What we know for sure is that time is intricately tied to the fabric of space and the very structure of the cosmos. Whether we look at the birth of the universe, the workings of black holes, or the effect of gravity on time's flow, it's clear that time is not a fixed, unchanging entity, but a dynamic, evolving feature of the universe. As scientists continue to explore the mysteries of time, from quantum gravity to the origins of the universe, we are constantly forced to challenge our assumptions and rethink our understanding of what time truly is. The more we learn, the more we realize that time is not just an abstract concept. It is a fundamental aspect of the universe, woven into the very fabric of reality itself. Whether time is an illusion, a product of quantum fluctuations, or a deeply ingrained feature of the cosmos, one thing is certain: the story of time is far from over. When we think of time, we tend to imagine it as an unyielding force, flowing forward with the inevitability of a river. But in the world of quantum mechanics, time doesn't always behave like that. In fact, the concept of time in quantum mechanics is one of the most perplexing and thought-provoking aspects of modern physics. It challenges our everyday understanding of how time works and opens up the possibility that time may not always move in one direction at all. One of the most intriguing perspectives on the arrow of time in quantum mechanics comes from physicist Timothy Maudlin. Maudlin has written extensively on the irreversibility of certain quantum processes, highlighting how, in some cases, time behaves differently at the quantum level than it does in the macroscopic world we experience. In classical physics, we think of time as flowing uniformly, from past to present to future, with processes happening in a specific irreversible direction, like a cup of coffee cooling down or a ball rolling downhill. But in the realm of quantum mechanics, things get a lot stranger. In quantum theory, many of the equations that govern the behavior of particles are time-symmetric, meaning they don't prefer one direction over the other. If you reverse time in these equations, the system could still function the same way. For example, in the microscopic world, particles move in ways that are mathematically indistinguishable if time were reversed. So why then does time seem to flow forward in the everyday world, while at the quantum level, time seems more malleable? This is where Maudlin and other physicists have focused their attention. They argue that while quantum mechanics may allow for time reversibility in its equations, the real world isn't always as tidy. In quantum mechanics, certain processes seem to have a preferred direction of time. For example, when particles interact or decay, the process doesn't reverse itself. Once a quantum event happens, like a particle decaying or a photon being absorbed by an atom, it doesn't spontaneously go backward. This process, called irreversibility, helps us understand why we perceive time as moving forward, despite the symmetry in the underlying quantum equations. But what if time itself is even stranger than we think? One of the most famous and controversial ideas in quantum mechanics is the many worlds interpretation, which suggests that the flow of time could split at every quantum interaction. According to this theory, every time a quantum event occurs, like a particle's position being measured or an atom absorbing light, the universe splits into different branches, each representing a different outcome of the event. In each branch, time continues to move forward, but each version of time exists independently in parallel universes. This idea, first proposed by physicist Hugh Everett in the 1950s, challenges the classical notion of time as a single, linear progression. Instead, it suggests that every quantum event creates a branching structure of time, with different outcomes in different worlds. Each branch of the universe follows its own timeline, but each one is just as real as the others. In this view, time is no longer just a one-way river, but a complex network of parallel timelines, all flowing in different directions but existing at the same time. While the many worlds interpretation is an exciting and mind-bending idea, it's also deeply controversial. Some physicists argue that the theory is overly complex and doesn't make predictions that can be tested or observed. Others suggest that while the many worlds model may sound far-fetched, it's one of the few interpretations that can reconcile quantum mechanics with the phenomenon of time. If the universe splits at every quantum interaction, then it could explain how quantum processes appear to have a direction in time, even though the fundamental equations are symmetric. Another concept that challenges our classical view of time is quantum entanglement. This is a phenomenon where two particles become linked in such a way that their properties are interdependent, no matter how far apart they are. If you measure the state of one particle, you can instantly know the state of the other, even if it's light years away. This strange connection between particles seems to transcend the normal limitations of time and space. When two particles are entangled, it's as if they share a moment in time, regardless of the distance between them. This creates what is sometimes called spooky action at a distance, a term famously coined by Albert Einstein. Entanglement doesn't just challenge our understanding of space, it also challenges our understanding of time. If two particles are connected in this way, how do we explain the simultaneous measurement of their states across vast distances? It seems as though these particles are communicating faster than the speed of light, which is famously prohibited by Einstein's theory of relativity. But while entanglement may defy our expectations about space, it also complicates our understanding of time. It suggests that time, at the quantum level, may not be as fixed or linear as we typically assume. The idea that time could behave differently at the quantum level has profound implications for our understanding of the universe. If quantum processes are non-linear, and time might flow in parallel branches with different outcomes, it challenges our classical conception of time as a single, unbroken thread. Time could, in fact, be much more flexible and complex than we ever imagined. This leads us to consider even more radical ideas, like the multiverse interpretation, which proposes that time exists in parallel, with different timelines unfolding in different worlds. One physicist who's explored this idea in great depth is David Deutsch, a British theorist who has been a leading figure in the development of the multiverse interpretation of quantum mechanics. Deutsch proposes that the many worlds theory is not just a speculative idea, but a potentially real feature of our universe. According to Deutsch, when quantum events occur, time branches into multiple possible outcomes, each of which leads to a different reality. In his view, these parallel worlds are just as real as our own, and time flows in each of them in slightly different ways. Deutsch's work suggests that the flow of time is not as simple as we experience it. Instead, time might be just one of many possible directions in which reality can unfold, depending on the choices made by quantum systems. This idea doesn't just stretch our understanding of time, it also challenges the very nature of reality itself. If time can branch out into multiple versions of the universe, then the flow of time we experience might be just one of many possible versions. As we explore these theories, whether it's the irreversibility of quantum processes, the branching nature of time in the many worlds interpretation, or the interconnectedness of particles through quantum entanglement, we begin to see that time is far more mysterious and complex than we ever realized. Time, at the quantum level, doesn't behave the way we expect. It might not be a simple flow from past to future, but a dynamic, shifting process that is deeply entangled with the very fabric of the universe. These ideas push us to reconsider everything we thought we knew about time. Is it really a simple, unidirectional force, marching forward as we experience it? Or is time something much more fluid, something that might exist in parallel, branch out in multiple directions, or even be an illusion? As physicists continue to explore the strange, fascinating world of quantum mechanics, one thing is certain: our understanding of time is far from complete. Time is not just a ticking clock, it's a key to unlocking the deepest mysteries of the universe. The arrow of time plays a fundamental role in the evolution of life on Earth. Just as time itself flows forward, so too do the processes that shape the diversity of life, pushing species to adapt and evolve in response to their ever-changing environments. But how exactly does time, this seemingly abstract concept, impact the way living organisms evolve? One of the key thinkers in this area was Konrad Lorenz, an Austrian zoologist who made significant contributions to the field of ethology, the study of animal behavior. Lorenz explored how evolutionary processes unfolded across time, especially in terms of natural selection. Natural selection, as we know, is the process by which traits that are advantageous for survival and reproduction become more common in a population over generations. This process occurs over long periods of time, as species gradually adapt to their environments. But Lorenz's work went deeper, examining how the evolution of behavior is shaped by time as well as environmental factors. Lorenz proposed that animals, like humans, are shaped not just by their physical traits, but also by behaviors that develop and adapt over time. For instance, certain behaviors, such as imprinting in birds, are learned early in life and can have profound effects on the survival of the species. In this way, time becomes an essential factor in the evolutionary process, influencing not just the physical characteristics of organisms, but also the patterns of behavior that are passed down through generations. Yet, the relationship between time and evolution is not just about survival and adaptation, it is also influenced by complexity. This is where the work of physicist Stuart Kauffman enters the picture. Kauffman is known for his exploration of self-organizing systems, which are systems that spontaneously develop order and complexity without the need for a central controlling force. Self-organization is an important idea when considering the role of time in evolution. Kauffman proposed that life itself is an example of a self-organizing system, where the components of living organisms, cells, proteins, genes, interact in ways that give rise to ever more complex structures over time. Self-organization challenges the idea that evolution is always driven by random mutations and natural selection alone. Instead, Kauffman argued that the evolutionary process is also shaped by the tendency of systems to organize themselves over time, given the right conditions. This concept of self-organization suggests that life is not just the product of external environmental pressures, but also of internal processes that push the system toward greater complexity. Over time, as these self-organizing systems interact with their environments, they generate more and more sophisticated forms of life. This idea fits neatly into the broader discussion of time and entropy. As we've seen, the second law of thermodynamics tells us that entropy, or disorder, naturally increases over time in closed systems. Yet, in living systems, entropy does not simply lead to chaos. Instead, life appears to work against this trend by maintaining a state of order. How can this be? Enter the concept of negentropy, a term that refers to negative entropy. Essentially, the order within living systems that counteracts the tendency toward chaos. The physicist Erwin Schrödinger, in his famous book What is Life, explored this idea in great depth. Schrödinger suggested that living organisms maintain their order by feeding on negative entropy from their surroundings. This process allows living systems to stay organized and functional in a universe that is constantly moving toward disorder. For example, when we eat food, we are taking in energy that our bodies use to maintain order within our cells and organs. This energy intake keeps us alive and functioning, even as the broader universe moves toward increasing entropy. Schrödinger's concept of negentropy highlights the interplay between life and time. Life depends on time to take in energy, organize it, and maintain structure, all while working against the ever-present march of entropy. In this way, living systems manage to preserve order in a world that is, on the whole, becoming more disordered. Over time, this process has allowed organisms to evolve from simple single-celled life forms into the complex array of species we see today. Time, in this sense, is not just a passive backdrop to evolution, it is an active force that shapes the development of life. The flow of time allows for the gradual accumulation of complexity, pushing living systems to become ever more sophisticated and better adapted to their environments. But while negentropy helps explain how living systems maintain order, it also raises more questions about the relationship between time and evolution. If life is constantly working to maintain order, what happens when those systems fail? How does time influence the decline of species and the eventual extinction of life forms? As we explore these questions, it becomes clear that time's role in evolution is not just about the rise of complexity, but also the eventual breakdown of systems over time. Time is also central to understanding the pace at which evolution happens. While changes in a species can take many generations to manifest, there are instances where evolutionary change seems to happen more rapidly. These periods of rapid evolution, known as punctuated equilibrium, challenge the traditional view that evolution is a slow, steady process. Instead, punctuated equilibrium suggests that species remain relatively stable for long periods, but then undergo rapid bursts of change in response to significant environmental shifts. These bursts of change, which can happen over just a few generations, highlight the role that time plays in shaping the evolutionary process. The timing of environmental changes, whether gradual or sudden, can significantly influence the course of evolution. In some cases, these rapid bursts of evolutionary change may be triggered by catastrophic events, such as asteroid impacts or drastic shifts in climate. These events create new pressures on species, forcing them to adapt quickly or face extinction. In this way, time becomes a force that drives the evolutionary process, not just through gradual changes, but also through sudden, transformative events that push life in entirely new directions. This brings us back to the concept of time as a driving force in the universe. Just as the second law of thermodynamics suggests that entropy increases over time, time also provides the backdrop for life to organize itself, adapt, and evolve. The flow of time allows for the gradual accumulation of complexity, the maintenance of order in living systems, and the occasional bursts of change that propel species into new forms. As we consider the interplay between time, entropy, and evolution, we see that time is not just a passive observer, it is a force that shapes life itself. From the self-organizing principles that drive the complexity of life to the negative entropy that helps living systems maintain order, time plays a central role in the ongoing process of evolution. Whether through gradual adaptation or rapid bursts of change, time is the thread that weaves the story of life, guiding it through cycles of growth, adaptation, and transformation. And as life continues to evolve, time remains the constant force that drives its progress, pushing living systems toward ever greater complexity and new forms of existence. The relationship between time and causality has been one of the central themes in philosophy and science for centuries. At its most basic, causality, the principle that every effect has a cause, is what allows us to understand the flow of time. It gives structure to our experience, telling us that events unfold in a particular order. One thing leads to another. Without causality, time would be an indistinct blur of unrelated events. It's causality that allows us to distinguish the past from the future, the cause from the effect. However, the concept of causality is not as straightforward as it might seem. In classical physics, causality was a given. Sir Isaac Newton's laws of motion, for example, describe a deterministic universe, where every action has a corresponding reaction, unfolding in a clear and predictable manner. The motion of planets, the fall of an apple, and even the motion of everyday objects could all be traced back to specific causes. Time, in this classical view, moved forward in one direction, with events happening in a logical sequence. Causes precede effects, and time itself flows in an orderly fashion. But as we moved into the realm of modern physics, the relationship between time and causality became less certain. The work of philosophers like David Hume raised significant questions about the very nature of causality. In the 18th century, Hume expressed skepticism about the idea of causality as a fundamental principle. According to Hume, we can never directly observe a causal connection between events. What we perceive as causality is merely a habit of thought, based on the consistent patterns we see in the world. When we see one event follow another repeatedly, we assume that one causes the other, but we don't have any direct evidence to prove that the cause and effect are truly linked in a necessary way. Hume's famous problem of induction suggests that we can never be entirely sure that the future will resemble the past, no matter how many times we've seen the same sequence of events. While Hume's critique of causality challenged the philosophical foundation of time, it also paved the way for deeper inquiries into the nature of time and causality in modern physics. In the 20th century, the advent of quantum mechanics and relativity forced scientists to reconsider the basic assumptions about how time and causality work. For instance, in quantum mechanics, events at the microscopic level seem to occur without clear deterministic causes. Particles can behave unpredictably, and events seem to be governed by probabilities rather than certainties. This raised new questions. If quantum events are not fully deterministic, does that mean time doesn't flow in a fixed direction? If causality breaks down at the quantum level, how does it influence the broader picture of time's flow? One physicist who addressed these questions was Richard Feynman, a Nobel laureate and one of the most influential figures in quantum mechanics. Feynman introduced a unique perspective on causality through his work on the path integral formulation of quantum mechanics. Feynman's approach considered all possible paths that a particle could take to move from one point to another, with each path having a certain probability. His view of causality in quantum mechanics is different from classical physics. Rather than thinking of a particle's path as being determined by one cause, Feynman's formulation suggests that all possible paths contribute to the final outcome, with probability playing a key role. Feynman's work revealed a crucial feature of quantum events. At the fundamental level, particles don't follow a single, well-defined path, but instead explore many possibilities. This raises the question of whether causality, as we understand it, even applies at the quantum level. If multiple potential outcomes exist simultaneously, how does causality function? In this quantum framework, causality is not as straightforward as a direct cause leading to a clear effect. Instead, the relationship between events is probabilistic, and time, at the quantum level, appears to be far more fluid and uncertain than in classical physics. But while quantum mechanics challenges our classical understanding of causality, it also opens up exciting new possibilities for how we think about the relationship between time and cause. One theory that builds on this idea is the concept of closed time-like curves, or CTCs. CTCs are solutions to Einstein's equations in general relativity that allow for time to loop back on itself, creating a kind of closed loop in the timeline. In this model, time becomes cyclical. An effect can, in theory, be its own cause. The implications of CTCs are profound. If time can loop back on itself, it could allow for paradoxes like the famous grandfather paradox, in which a person travels back in time and prevents their own existence by altering events in the past. The idea of CTCs challenges the very nature of causality. If time is truly circular in certain regions of space-time, it suggests that causality might not always work in one direction, as we assume. Instead, it raises the possibility that the future can influence the past, creating a feedback loop in which causes and effects are reversed or entangled. Some physicists, such as Kip Thorne, have explored the theoretical possibilities of time travel through wormholes and CTCs, adding another layer of complexity to our understanding of causality and time. Another thinker who has delved into the nature of time and causality in a different way is Raphael Sorkin, a theoretical physicist known for his work on causal set theory. Causal set theory is an approach to quantum gravity that applies the principle of causality to the structure of space-time itself. Instead of viewing space-time as a smooth continuum, as Einstein did in general relativity, causal set theory suggests that space-time is composed of discrete events, connected by causal relationships. In this view, time doesn't flow smoothly or continuously, but rather unfolds through a series of events, with each event causally related to those that came before it. Sorkin's approach offers a fresh perspective on time's flow by suggesting that space-time is fundamentally discrete, not continuous. In this model, causality is the bedrock of space-time, with the very structure of the universe emerging from causal relationships between individual events. This challenges the traditional view of time as a fluid, continuous force, and suggests that time may, in fact, be a more granular phenomenon. Causal set theory also connects to quantum mechanics, as it proposes that quantum gravity might emerge from the discrete, causally related events in space-time. If we take all of these ideas together, Feynman's probabilistic view of causality in quantum mechanics, Sorkin's causal set theory, and the possibility of closed time-like curves, we see a picture of time and causality that is far more complex than our everyday experience would suggest. In classical physics, time is often treated as a continuous unidirectional flow, but in the quantum realm and at the extremes of space-time, the relationship between cause and effect is far more intricate and mysterious. In a universe where causality may break down in quantum events or be bent and warped by the structure of space-time, the flow of time becomes less predictable and more open to interpretation. What does this mean for the nature of time's arrow? If causality itself can be violated, does it suggest that time too can be something other than a one-way progression? As we explore these theoretical possibilities, we're confronted with a vision of time that is much more fluid, interconnected and multifaceted than we could have imagined. As scientists continue to probe the mysteries of causality and time, whether through the strange behaviors of quantum particles, the structure of space-time, or the speculative possibilities of time travel, one thing is clear. The relationship between time and causality is still an open question, one that continues to challenge our deepest assumptions about the universe and our place within it. Time may not be the straightforward, unidirectional force we think it is. Instead, it could be a far more complex and dynamic feature of the universe, governed by the same principles of causality that shape the very fabric of reality itself. Our experience of time is uniquely personal, and much of it comes down to how our brains perceive its passage. Time is often thought of as a steady, unchanging force, ticking away relentlessly. But when we take a closer look at how we experience it, we see that it's far more fluid than we might expect. The way time feels to us, the way we perceive the past, the present, and the future, can shift dramatically depending on our mental state, our emotions, and even the way we store memories. One important way our brains process time is through the concept of subjective time. Subjective time is the personal, individual experience of time's passage, which can be very different from the objective time measured by clocks. John Weirden, a psychologist, explored this idea in his work on how we perceive time. He found that our sense of time can vary greatly from one person to another, and even within the same individual under different circumstances. For example, when we are relaxed and at ease, time often seems to pass more quickly. But when we are anxious, bored, or in pain, time seems to drag on endlessly. This variation in time perception is rooted in the way our brains process and respond to external stimuli. Weirden's research showed that the brain doesn't simply track time as a constant, unchanging flow. Instead, it reacts to our mental and emotional states, making time feel longer or shorter, based on how engaged we are in the moment. This subjective perception of time also varies across species. In humans, for example, time feels different depending on age, culture, and individual experiences. A child, for instance, often experiences time as moving slower than an adult, largely because for a child, every year represents a larger proportion of their life than it does for an adult. The more life experience we accumulate, the faster time seems to pass, as we compare the present moment to all the moments that have come before. Daniel Kahneman, a Nobel laureate and psychologist, further expanded on our perception of time, particularly in relation to emotional experiences. Kahneman is known for his research on how our brains interpret and store memories of time. His work on prospective memory and retrospective memory highlighted how we not only experience time in the moment, but also how we remember it. When reflecting on past events, our minds tend to focus on the most emotionally intense moments, distorting our perception of the duration. This is known as the peak end rule, a psychological phenomenon where we tend to remember an experience by its most intense moment and its conclusion, rather than the experience as a whole. For example, a vacation might seem to have passed quickly, even if it lasted a week, if the final day was particularly enjoyable. This distortion happens because our brain processes the emotional highs and lows more vividly than the mundane moments in between, affecting how we perceive the passage of time. Kahneman also explored how our perception of future events can shape our sense of time. When we anticipate something exciting like a vacation or a big event, time often feels like it's moving slowly. We're eagerly waiting for something that hasn't yet happened, and that anticipation can make the present moment seem prolonged. On the other hand, when we dread an event such as a long meeting or an uncomfortable situation, time can feel like it stretches endlessly as our mind dwells on what's to come. But time isn't just about how we remember the past or anticipate the future, it's also how our brains perceive the present. V.S. Ramachandran, a renowned neuroscientist and philosopher, proposed an interesting theory about how our brain processes time in the present moment. He suggested that our experience of time is inherently linked to the brain's need to organize sensory information and anticipate future events. For Ramachandran, our perception of time is not simply a passive recording of events, but a proactive process. The brain is constantly predicting what will happen next and adjusting its sensory inputs accordingly. This ongoing prediction allows us to make sense of the continuous flow of information that bombards us every moment. In Ramachandran's view, the brain doesn't just process time by observing it. It creates time through its predictive mechanisms. We don't experience every single moment in its raw detail. Instead, the brain fills in the gaps, predicting what will happen next based on patterns it has observed in the past. This is why our perception of time can feel seamless and continuous, even though it's actually an intricate mental construction. Ramachandran also suggested that this predictive nature of the brain's time perception could explain why time feels differently depending on the complexity of the task at hand. For example, when we are deeply focused on a task or a problem, time seems to slow down as the brain is processing more information and making more predictions. When we're less engaged, such as during idle moments or when we're waiting for something, time appears to speed up as fewer predictions need to be made and our brain enters a more passive mode. The idea that time perception is connected to the brain's ongoing predictions ties into some of the more abstract theories of time. Some philosophers and neuroscientists argue that the experience of time is more than just a reflection of objective reality. It's an active process that the brain constructs based on its expectations and sensory input. Time, in this view, is not just something that happens to us, but something our minds create in response to the world around us. This active construction of time is a fascinating area of study, especially when we consider the implications for the future of neuroscience and psychology. As we continue to explore how the brain processes time, we might discover new ways to manipulate and understand our perception of time, whether to slow it down or make it feel more expansive. If time is something the brain actively constructs rather than passively observes, perhaps we can influence how we experience it through mental training or changes in our environment. As we wrap our thoughts around time's psychological dimension, we see that time is not just a passive ticking of the clock. It is deeply interwoven with our mental states, memories, and anticipations. From the way we perceive time differently at different ages to how our emotional experiences shape our memories, time is something that flows in a way that is uniquely ours. The brain, with its complex and intricate processes, takes this universal phenomenon and shapes it into a personalized experience. Time is as much about how we feel it as it is about the objective passage of seconds, minutes, and hours. And in this way, our experience of time is both deeply rooted in biology and yet powerfully influenced by our consciousness and emotions. Time travel is one of those fascinating concepts that seems to blur the lines between science and science fiction. For decades, it has captivated the imagination of writers, filmmakers, and thinkers alike. From the classic time machine invented by H.G. Wells in his novel The Time Machine to the more recent depictions in films like Back to the Future, the concept of jumping through time has become a staple of pop culture. But while these stories entertain us, they also raise serious questions about the very nature of time itself, and whether it's even possible to break the rules of time as we know them. The idea of time travel, at least as we envision it in fiction, is often depicted as the ability to move backward or forward in time, altering events along the way. One of the most famous aspects of these stories is the potential for paradoxes, situations where time travel leads to contradictions or loops that seem impossible to resolve. The most well-known of these paradoxes is the grandfather paradox, which raises the question, what happens if you travel back in time and prevent your grandfather from meeting your grandmother? If this happens, you would never be born, so how could you have travelled back in time in the first place? This creates a logical inconsistency, a loop that can't be resolved. The grandfather paradox is just one example of the many puzzles that arise when we consider the possibility of time travel. If we could change events in the past, how would that affect the present? Would the very act of travelling through time cause alterations to the course of history? The implications of such paradoxes seem to suggest that time travel, if possible, could lead to a kind of chaos, where the linear flow of time is disrupted and the cause and effect relationships we rely on in everyday life break down. But while these paradoxes make for good storytelling, scientists have also considered whether time travel is even feasible within the framework of modern physics. A key idea in many discussions of time travel comes from the theory of general relativity, developed by Albert Einstein in the early 20th century. According to general relativity, time and space are not separate entities, but are woven together into a four-dimensional fabric known as space-time. This fabric can be warped by the presence of mass and energy, which is why the Earth orbits the Sun and why light bends as it passes near a massive object, such as a star or a black hole. One of the fascinating implications of general relativity is the possibility of wormholes. A wormhole is a theoretical passage through space-time that could, in theory, connect two distant points in space and time. Imagine a tunnel with two openings, one on Earth and the other somewhere far away, perhaps on the other side of the galaxy or in a different time altogether. If we could travel through this wormhole, we might be able to jump between different points in space and time instantly, without having to traverse the vast distances of the universe. Wormholes are a tantalizing idea, but there are serious scientific challenges that make their existence highly speculative. First, wormholes are not something we can just create at will. They would require massive amounts of energy to form and would likely be unstable, collapsing before anything could pass through them. Furthermore, if wormholes could exist, they would need to be incredibly small, on the scale of subatomic particles. It's still unclear whether such structures could exist in a form that would allow for the practical travel we often see in science fiction. Even if wormholes did exist and could be stabilized, they still pose a major problem for time travel. According to the equations of general relativity, a wormhole could theoretically allow for time travel to the past, but only under very specific conditions. This leads us into the realm of closed time-like curves, or CTCs, which are solutions to Einstein's equations that describe loops in space-time. A CTC would allow an object to travel in such a way that it eventually returns to its starting point in both space and time, essentially creating a time loop. However, CTCs raise even more paradoxes, as we saw with the grandfather example. If time loops around itself, what prevents you from making changes to the past that would alter the future? And if the future is altered, how does that affect the original loop? This is where things get truly complicated, and it's not clear whether CTCs are physically possible, or whether they would even make sense within the laws of physics. For all the speculative ideas about wormholes and time loops, there's another important question. Can we even travel faster than light? One of the key principles of Einstein's theory of relativity is that nothing can travel faster than the speed of light. This creates a major obstacle for time travel because in many time travel theories, moving faster than light is necessary to jump between different times. If we can't exceed the speed of light, it seems that time travel, at least as we imagine it in science fiction, would be impossible. However, there are some theoretical ideas that allow for effective faster-than-light travel without violating the laws of relativity. One such idea is the concept of the Alcubierre drive, named after Mexican physicist Miguel Alcubierre. The Alcubierre drive suggests that a spacecraft could achieve faster-than-light travel by contracting space in front of it and expanding space behind it, creating a warp bubble that moves the spacecraft faster than light without actually moving the spacecraft itself. This concept doesn't break any fundamental laws of physics, but it does require enormous amounts of energy, far beyond anything we currently know how to generate. Even if these theoretical concepts of time travel were possible, there would still be the question of how time travel might affect the arrow of time. If time travel is possible, could it cause changes in the past that would disrupt the progression of time as we know it? Could it cause paradoxes, like the grandfather paradox that break the fundamental rules of cause and effect? Would it be possible to change history, or would time correct itself, preventing any changes from sticking? One way to think about this is through the lens of the many worlds interpretation of quantum mechanics, which suggests that every time an event occurs that has multiple possible outcomes, the universe splits, with each outcome occurring in a separate parallel timeline. In the context of time travel, this could mean that when you travel back in time and make a change, you're not actually changing the past in your original timeline. Instead, you're creating a new timeline, a parallel universe where the changes you've made take place. This interpretation provides a potential solution to time travel paradoxes, but it also raises its own questions about the nature of reality and the consequences of interfering with time. While the idea of travelling through time remains firmly in the realm of theoretical physics and science fiction, it does raise intriguing questions about the nature of time itself. Is time truly a linear progression, or could it be more flexible than we think? Could we ever overcome the barriers that seem to prevent time travel, such as the speed of light or the laws of causality? And if we could travel through time, would we be able to change the past, or would the arrow of time protect its course, keeping the universe on track? For now, time travel remains one of the great mysteries of science. While we don't have the answers, the exploration of these ideas invites us to rethink the nature of time, space, and the universe itself, and to wonder what might be possible if we ever learn how to break through the boundaries of time. When we think about black holes, we often picture their immense gravity pulling everything, including light, into an invisible void. But black holes don't just affect matter, they also have a profound impact on time itself. Time behaves very differently near a black hole than it does on Earth or anywhere else in the universe. Understanding how time behaves around black holes gives us valuable insights into the very nature of space-time and its relationship to gravity. At the heart of this strange behavior lies the concept of time dilation. Time dilation is a phenomenon predicted by Albert Einstein's theory of general relativity, and it occurs when the presence of a massive object, like a black hole, warps space-time. This warping affects the passage of time, causing it to slow down as you get closer to the source of gravity. Near a black hole, this effect is particularly pronounced. As you approach the event horizon, the point beyond which nothing can escape the black hole's gravitational pull, time seems to slow down dramatically. From the perspective of an outside observer, time near the event horizon appears to slow almost to a standstill. Imagine watching someone fall into a black hole. From your viewpoint, their descent would seem to slow down as they approach the event horizon, and they would appear to freeze in place just before crossing it. However, from the perspective of the person falling in, time would continue to pass normally, but they would be moving toward a point where space itself behaves in ways we can't fully predict. The closer you get to the event horizon, the stronger the gravitational forces become, and the more distorted time becomes. At the event horizon itself, time theoretically comes to a complete stop, at least as observed from the outside. In this way, the event horizon is not just a physical boundary around a black hole, but also a boundary that marks a dramatic shift in the way time functions. Once you cross that threshold, you are beyond the reach of any information that could escape the black hole, and the normal rules of time seem to break down. This warping of time near black holes ties directly into the concept of space-time itself. According to general relativity, space and time are not separate, but form a single unified fabric. This fabric is warped by mass and energy, and the more massive the object, the greater the distortion. Black holes, with their incredible density and gravitational pull, create the most extreme warping of space-time known to science. This leads to the slowdown of time, as gravity becomes more and more intense the closer you get to the black hole's core. Physicist Kip Thorne, who is widely regarded as one of the leading experts on the science of black holes, has explored how the warping of space-time near black holes could be used to examine the nature of time travel and even time reversal. Thorne's work has shown that under certain conditions it might be possible to use the gravitational fields of black holes to bend space-time in such a way that time travel could occur. If we could harness the curvature of space-time around a rotating black hole, known as a Kerr black hole, we might be able to create a sort of time machine, where an object or even light could travel back in time. This idea is still highly speculative, of course. The energy required to manipulate space-time in such a way would likely be beyond anything we can generate. But the fact that black holes create such extreme distortions of time is an indication of just how deeply intertwined space and time are, and how much we have yet to learn about time's true nature. Now, while the concept of time dilation is fascinating, it also brings us to an even more mind-bending phenomenon: spaghettification. Spaghettification, also known as the tidal force effect, occurs when an object falls into a black hole and experiences an enormous difference in gravitational forces between its top and bottom. This difference stretches the object in the direction of the black hole and compresses it in the perpendicular direction, much like how a piece of spaghetti is elongated when pulled. For anything approaching the event horizon of a black hole, this effect becomes more intense as it gets closer to the singularity, the point at the center of the black hole where all the mass is concentrated. This stretching effect would be catastrophic for any object, human or otherwise. As you get closer to the event horizon, the difference in gravity between your head and feet would increase so dramatically that it would rip you apart long before you could ever reach the center of the black hole. This spaghettification occurs because the gravitational pull on the side of you, closest to the black hole, is vastly stronger than the pull on the side farthest away. The result is a stretching and pulling effect that causes the object to be torn apart. While spaghettification is fascinating from a theoretical perspective, it also underscores the irreversible nature of black holes. Once something passes beyond the event horizon, it can never return. Not only does the intense gravity prevent anything from escaping, but the very structure of time is changed beyond that point. The arrow of time, the one-way flow of time, is fundamentally altered inside a black hole. Any attempt to reverse the flow of time within a black hole would violate the fundamental principles of thermodynamics and causality, making it one of the most extreme and irreversible environments in the universe. Despite the mind-bending nature of these effects, black holes also provide us with valuable insights into the nature of space-time and the laws that govern the universe. By studying the behavior of light, matter, and time near black holes, physicists can test the limits of our current understanding of general relativity and quantum mechanics. Black holes, in a way, serve as natural laboratories where the most extreme forces in the universe combine to reveal new insights about the nature of time, gravity, and the very structure of reality itself. In many ways, black holes represent a frontier in both physics and our understanding of time. The extreme warping of space-time near these cosmic giants raises profound questions about the directionality of time, its relationship with gravity, and the possibility of time travel. Whether through time dilation, spaghettification, or the more speculative idea of time loops, black holes push the boundaries of what we think is possible, inviting us to rethink everything we know about time's flow. The study of black holes continues to evolve, and as we gain more knowledge about these mysterious objects, thanks to groundbreaking research and tools like the Event Horizon Telescope, we may one day be able to unlock even more secrets about the nature of time itself. For now, we can only marvel at the incredible forces at work inside black holes and the mysteries they hold, as we continue to explore the deepest questions of physics and the universe. As we venture into the future of physics, one of the most exciting areas of exploration is the study of time. Time is a fundamental part of how we understand the universe, but we're only scratching the surface of what might be possible in terms of manipulating or controlling it. With advancements in technology, our ability to study time may one day allow us to experience it in entirely new ways, or even to control its flow. But along with this potential, there are also profound philosophical and ethical questions that arise, making the future of time both thrilling and daunting. For centuries, time was considered an immutable force, flowing in one direction, unaffected by our presence. But today we know that time is not as fixed as we once thought. Einstein's theory of relativity showed us that time is relative, dependent on factors like speed and gravity. It bends and stretches based on the conditions of the universe. But even that understanding may only be the beginning. The real challenge of manipulating time is understanding the very fabric of space-time itself, and how it behaves at both the cosmic and quantum scales. One of the most promising areas of research into the manipulation of time involves the study of exotic materials and phenomena like time crystals. Time crystals are a recent concept in physics that could change the way we think about time and energy. First proposed by Nobel laureate Frank Wilczek in 2012, time crystals are materials that, in theory, could exhibit time translation symmetry breaking. This means that they could oscillate between different states without using energy in the way that other systems do. Essentially, they could act as a kind of perpetual motion machine, oscillating in time without violating the laws of physics. While time crystals have only recently been realized in the lab, thanks to experiments at institutions like Google's Quantum AI Lab, they represent a tantalizing possibility for the future of time manipulation. In these experiments, researchers have created time crystals in quantum systems where they appear to oscillate in time in a manner similar to how crystals oscillate in space. This could lead to breakthroughs in quantum computing, where time crystals might be used to store and process information in ways that are currently unimaginable. While they don't allow us to travel through time or reverse its flow, they do hint at the possibility of controlling how time unfolds in certain systems. Another potential avenue for future breakthroughs is the manipulation of space-time itself. If we can find a way to control the curvature of space-time, perhaps through massive gravitational fields or by creating artificial wormholes, then we could theoretically manipulate the flow of time in ways that would allow for time travel or even time reversal. The idea of using black holes or other massive objects as a way to bend time has been a long-standing concept in both science fiction and theoretical physics. We've seen in earlier discussions that time slows down near black holes due to their extreme gravity. But what if we could use this effect more deliberately? One theory that could help guide our understanding is the idea of using rotating black holes, or Kerr black holes, to potentially allow for travel through time. These black holes spin, and in theory the rotation could create a wormhole or time loop that allows an object to travel both backward and forward in time. Kip Thorne, a prominent physicist, has explored these ideas in depth, suggesting that, under the right conditions, the warping of space-time around a rotating black hole could create a path through time. While these ideas remain firmly in the realm of theory, they demonstrate that understanding and possibly controlling the flow of time is not as far-fetched as it may once have seemed. The more we learn about time, the more we begin to see that our future may hold incredible possibilities for how we experience it. If we could one day manipulate time, it would open up possibilities beyond just time travel. Imagine being able to slow down time for a particular moment or area, allowing you to experience an event in slow motion. This could have profound implications for everything from medicine to entertainment to even the way we perceive our daily lives. Imagine being able to pause time, not just in science fiction, but in reality. For example, you could use a time dilation effect to pause critical moments, giving yourself more time to make decisions or act. Yet, the potential for manipulating time raises serious ethical and philosophical questions. What would it mean for society if we could control time? How would it affect our sense of reality and our perception of life itself? If time could be manipulated, would it erode our understanding of causality, our understanding that every event is linked to something that came before it? The very nature of time is central to our understanding of existence. Manipulating it could change our world in ways we can't yet predict. Consider the ethical ramifications. If we could reverse time, would we undo mistakes or tragedies? Could time be used to right wrongs, or would it open the door to unforeseen consequences? If someone had the ability to reverse time, would they be able to avoid painful events in their lives? And if they did, how would that change the person they were destined to become? These questions touch on deep philosophical themes about fate, free will, and the nature of human existence. As we look forward, the potential for space-time exploration is also on the horizon. Space travel, particularly the idea of traveling faster than light, could fundamentally change how we experience time. If we could someday master faster-than-light travel, we might be able to visit distant parts of the universe and even witness events from the past or future. While this remains highly speculative, the idea that time could be experienced differently in different regions of space is one of the most exciting prospects of future science. This brings us back to the question, what is time, and how might we experience it in the future? Time, as we understand it now, seems like a constant, unchanging feature of the universe. But the more we learn, the more we realize that time is not as straightforward as it seems. As our understanding of quantum mechanics, relativity, and the structure of space-time deepens, we may one day unlock the mysteries of time itself, allowing us to manipulate it in ways that once seemed impossible. In the future, we may find ourselves experiencing time in ways that we can't even imagine today. Time could be something we shape, something we bend, something we control. Whether through the study of time crystals, the manipulation of space-time, or even time travel, the future of time holds endless possibilities. And as we continue to explore the nature of time, we might just find that our understanding of the universe, and our place within it, becomes even more wondrous than we ever thought possible. From the very beginning of human civilization, time has been both a mystery and a tool. Our ancestors, living in an environment governed by the cycle of day and night, the seasons and the movement of celestial bodies, quickly realized the need to understand and measure time. This basic need gave rise to one of humanity's most essential and powerful inventions, the concept of timekeeping. But how we measure time has changed dramatically over millennia, from simple observations of the sun's position in the sky to the highly precise atomic clocks we use today. In ancient civilizations, timekeeping was closely linked to the natural world. The Egyptians, for example, used sundials to measure the passage of the day. By observing the shadow cast by a stick, or gnomon, placed upright in the ground, they could estimate the time based on the position of the sun. The Egyptians and later the Greeks also created water clocks, which allowed time to be measured at night or during cloudy days when the sun wasn't visible. These early tools were rudimentary, but they represented a critical step forward in humanity's ability to structure life around time. As civilizations grew more complex, the need for more accurate and standardized timekeeping became clear. The ancient Babylonians introduced a system based on the number 60, dividing the day into 24 hours, each hour into 60 minutes, and each minute into 60 seconds, a system we still use today. By the time of the ancient Romans, mechanical clocks were becoming more sophisticated, though they were still powered by water or weights, and required manual resetting. However, it wasn't until the Middle Ages that the first true mechanical clocks were developed in Europe. These early clocks were powered by gears and weights, and used a system of escapement, a mechanism that allowed the clock to regulate the flow of time. These clocks were often found in church towers and were used to regulate daily activities such as prayer times and market hours. Over time, the technology improved, with the development of more precise escapements and the introduction of pendulums in the 17th century. The pendulum clock, invented by Dutch scientist Christian Huygens in the year 1656, became the standard for precision timekeeping, allowing for remarkably accurate measurements of time. In the 19th and 20th centuries, as industrialization and global trade grew, the need for even more precise timekeeping became urgent. The invention of the chronometer, a highly accurate timekeeping device for navigating the seas, was a game changer. This advancement led to the creation of synchronized time across regions, which was crucial for the growing railroad networks in the United States and Europe. Time zones, standardized by Sir Sandford Fleming in the late 19th century, were introduced to make sure that train schedules could be reliably coordinated across vast distances. The most significant advancement in timekeeping, however, came with the development of atomic clocks. Unlike mechanical clocks, which rely on physical movements, atomic clocks are based on the vibrations of atoms, specifically cesium atoms. These clocks are incredibly accurate, losing only 1 second every 100 million years. The discovery of atomic timekeeping in the mid-20th century revolutionized not just time measurement, but also technologies that rely on precise time, such as GPS systems and telecommunications. In fact, the Global Positioning System, which helps millions of people navigate the world every day, depends on the synchronization of atomic clocks across a network of satellites in orbit. These advances in timekeeping are more than just technical achievements. They have shaped the way we live and interact with one another. The ability to measure time with such precision has had profound effects on technology, science, and culture. Consider the way our understanding of time has driven progress in virtually every field of science, from astronomy to particle physics. Time, as we now measure it, is essential to understanding the behavior of the universe on every scale. From the motions of galaxies to the behavior of subatomic particles, time is also fundamental to the development of modern technology. The clockwork of the digital age relies on the precise measurement of time to keep everything in sync. The internet, for example, depends on the accurate timing of data transmission to ensure that information is sent and received without delay. And in the realm of quantum computing, where computations happen on an incredibly small scale, even the tiniest misstep in time measurement could cause significant errors. But timekeeping doesn't just shape the world of science and technology. It has also had profound effects on society and culture. Our modern lives are structured around the idea of precise time. Work schedules, school hours, and social interactions are all governed by the ticking of the clock. The concept of time is money, popularized during the Industrial Revolution, became an essential part of capitalist economies, where productivity was measured in terms of time. The efficiency of labor was closely tied to the ability to organize time in a standardized, predictable way. Our relationship with time also affects our emotional and psychological well-being. Think about how time is often viewed in the context of urgency, how deadlines, appointments, and the constant rush to make the most of every minute can create stress and anxiety. On the other hand, time can also provide structure and meaning. We celebrate milestones, from birthdays to anniversaries, marking the passage of time as something to be cherished. Time is also a key element in the way we form memories, with the events of the past shaping our present identity. The manipulation of time, how we experience it, measure it, and even control it, also plays a role in shaping human advancement. Technologies that allow us to measure time with precision have revolutionized industries and changed the way we perceive the world. Yet the way we perceive time is not only a matter of precision, but also perception. Our experience of time can vary depending on our circumstances. For example, time often seems to move more slowly when we're bored or anxious, but when we're engaged in something exciting or joyful, time can appear to fly by. This subjective experience of time can influence how we live our lives, how we work, and how we interact with others. The social constructs that surround time also shape our experiences. For instance, the concept of saving time or spending time reflects the value we place on time as a limited resource. In many ways, our modern obsession with time efficiency has led to a faster-paced lifestyle, one that constantly pushes us toward achieving more, doing more, and experiencing more within ever-shrinking windows of time. This drive for efficiency has had both positive and negative consequences, from technological innovation to social alienation and burnout. Yet, it's important to recognize that time is not just an external force we measure and manage. It's something deeply tied to our internal lives. It's the way we remember our past, live in the present, and anticipate the future. Our ability to control and organize time has allowed us to achieve incredible feats, but it has also shaped the way we relate to the world and to each other. As we continue to refine our understanding of time and improve our methods of measuring it, we may one day unlock new possibilities for how we experience and interact with time, perhaps even allowing us to manipulate it in ways that today seem unimaginable. Time, in many ways, is not just something we experience, it's something we've created, organized, and shaped to serve our needs. It's both a tool and a challenge, a constant companion in the story of human civilization. And as we continue to evolve, our relationship with time will continue to shape the future in ways we can only begin to imagine. Time is, at its core, a fundamental aspect of the universe, something we experience every moment, yet struggle to fully grasp. But what happens when we think about time not just as an external force, but as something deeply intertwined with our consciousness? After all, our awareness of time, our experience of it, and our ability to reflect on past and future moments are all intrinsically connected to the way our minds work. Consciousness and time are so intertwined that it's difficult to imagine one without the other. Our awareness of time shapes how we perceive the world around us. When we look at the clock, we see hours, minutes, and seconds pass. But that clock is only one way of measuring time. What's happening in our minds during those moments of awareness? How do we experience time passing in our subjective reality? And what does that tell us about the relationship between consciousness and the flow of time? One of the most interesting aspects of how we experience time is the way it changes in different states of consciousness. For instance, when we sleep, time seems to behave very differently. The passage of time during sleep can be hard to grasp. Minutes feel like hours, and hours feel like minutes. We may wake up feeling as though we've been asleep for only a short time, only to find that the clock tells a different story. Similarly, when we meditate or enter altered states of consciousness, our perception of time can shift dramatically. In deep meditation, some people report losing all sense of time, entering a state where past, present, and future seem to collapse into one. This phenomenon suggests that time may be as much a construct of the brain's awareness as it is a measure of external reality. This connection between time and consciousness has been explored by many neuroscientists. One of the leading figures in this area is Antonio Damasio, a Portuguese neuroscientist known for his work on consciousness and the brain. Damasio has proposed that our sense of time is deeply tied to our ability to construct a sense of continuity in our experience. For Damasio, time isn't something that exists independently of us, but rather is something the brain constructs through its ongoing processing of sensory information. According to his theories, consciousness arises from the brain's continuous integration of past experiences, the present moment, and its predictions about the future. This ongoing process of integration is what gives rise to our awareness of time's flow. Damasio has also suggested that the brain doesn't just process time as a passive observer. Instead, the brain actively creates a sense of time by maintaining continuity in our conscious experience. This means that time, in some sense, is as much a product of the mind as it is a feature of the external world. Our perception of time doesn't just depend on external cues, like the ticking of a clock or the passing of seasons, but is also shaped by the brain's internal processes. As we move through life, our mind constantly updates its internal sense of time, allowing us to keep track of events, anticipate the future, and make sense of the present. Yet, while time may be fundamentally linked to consciousness, there are still deeper questions to explore about how time is experienced at the most fundamental level. Some theories in quantum mechanics suggest that time itself may be something much more fluid and complex than our everyday experience would suggest. For example, physicists like Roger Penrose and Stuart Hameroff have proposed theories that link time and consciousness to the fabric of the universe itself, suggesting that the flow of time may emerge from the fundamental processes of the brain at a quantum level. Penrose, a British theoretical physicist, is perhaps best known for his work on the connection between consciousness and quantum mechanics. He suggests that consciousness arises not just from neural activity in the brain, but from quantum processes occurring at the subatomic level. In this view, the brain's neurons aren't just electrical circuits processing information. They also tap into a deeper quantum level of reality, where the flow of time may not be as linear or straightforward as we experience it. Penrose's theories propose that time may not even exist in the traditional sense at the quantum level, but may emerge from the interactions between quantum particles in the brain. Stuart Hameroff, an American anesthesiologist and one of the co-developers of the orchestrated objective reduction theory of consciousness, has worked alongside Penrose to suggest that the brain's microtubules, tiny, tube-like structures inside neurons, may act as quantum computers. According to Hameroff and Penrose, these microtubules may be capable of processing information in a quantum way, allowing consciousness to emerge as a result of quantum interactions. In this model, the flow of time might not be a simple, continuous progression, but could emerge from complex quantum processes that occur within the brain. If time is an emergent property of consciousness, this raises profound questions about the nature of both time and consciousness. Is time truly fundamental to the universe, or is it simply a byproduct of our conscious experience? One of the most provocative aspects of this theory is the idea that time, rather than being a universal constant, may be something that arises from consciousness itself. In this view, time might not be an intrinsic feature of the universe, but rather something that our minds create in order to make sense of the world. This suggests that consciousness is not just a passive observer of time, but rather an active participant in its creation. Our perception of time could be one of the brain's most important functions, an essential process that allows us to experience the world as a coherent, continuous reality. If time is indeed an emergent property of consciousness, then the nature of time could be different for each conscious being. Just as our subjective experiences of time can vary depending on our mental state, so too could the way time flows or is perceived be different for different beings, or even different levels of consciousness. This could lead to radically different understandings of time's role in the universe. As we delve deeper into the nature of time and consciousness, it's clear that the relationship between the two is more complex than we may have imagined. Time is not simply something that happens to us, it is something we experience through our conscious awareness. From the construction of continuity by the brain to the potential quantum basis for time's flow, our understanding of time is evolving in ways that challenge the fundamental assumptions we've held for centuries. Whether time is a basic feature of the universe or an emergent property of consciousness, it's clear that time and awareness are intimately connected in ways that we're only beginning to understand. In the future, as neuroscience and quantum physics continue to advance, we may come to see time in an entirely new light, perhaps as a mental construct, a product of the mind's need to make sense of the world, or perhaps as something far more complex, intertwined with the deepest fabric of the universe. Either way, the journey to understand time and consciousness is one that will likely continue to reveal new mysteries and insights about the nature of our reality. The connection between space and time is one of the most profound insights in modern physics. For centuries, we understood space and time as separate entities. Space was the three-dimensional arena in which objects existed, and time was the separate linear flow in which events occurred. This neatly compartmentalized view of the universe held sway for a long time, but it was shattered with the advent of Einstein's theory of relativity, which showed us that space and time are intimately intertwined in a single entity, space-time. The theory of relativity revolutionized how we think about the cosmos. Rather than being two independent aspects of reality, space and time are combined into a unified framework, space-time, where both dimensions are inseparable. This idea wasn't immediately obvious, and it took the contributions of lesser-known figures like Hermann Minkowski to fully solidify the concept. Minkowski, a German mathematician, introduced the idea that time could be treated as a fourth dimension, much like the three spatial dimensions. By combining space and time in this way, Minkowski's work provided the mathematical foundation for Einstein's theory of relativity. He showed that the geometry of space and time could be represented as a four-dimensional continuum, where events are not located in just space or just time, but in both. Minkowski's concept of space-time is more than a mathematical abstraction. It has real, observable consequences. One of the most fascinating implications of space-time is the way that gravitational fields, like those created by massive objects such as planets or stars, warp both space and time. This phenomenon is known as space-time curvature and is at the heart of general relativity. Instead of thinking of gravity as a force pulling objects toward each other, as Isaac Newton described, Einstein's theory shows that massive objects like the Earth or the Sun curve the fabric of space-time around them, causing nearby objects to follow curved paths. This warping of space also alters the passage of time. The closer you are to a massive object, the more space-time is curved, and the slower time passes relative to someone farther away from that object. This effect, known as gravitational time dilation, has been confirmed through numerous experiments. For instance, clocks placed at higher altitudes, where gravity is weaker, tick faster than those at lower altitudes, where gravity is stronger. The difference is tiny but measurable with modern technology. On a much more extreme scale, near massive objects like black holes, this effect becomes far more pronounced. Time near a black hole slows down so dramatically that, from the perspective of an outside observer, anything approaching the event horizon, the boundary beyond which nothing can escape, appears to freeze in time. Black holes provide a fascinating example of how space and time are intricately linked. At the center of a black hole lies a singularity, a point where space-time becomes infinitely warped and the laws of physics as we understand them break down. Near this singularity, time doesn't just slow down, it behaves in ways that challenge our intuition. The intense curvature of space-time near a black hole creates a situation where the flow of time is drastically different from what we experience in less extreme environments. For an observer far from a black hole, the time near the event horizon would appear to slow down to a crawl. If someone were to fall into a black hole, they would experience time normally from their perspective, but from the outside world's view, their fall would seem to stretch on forever, frozen at the event horizon. This bizarre phenomenon illustrates just how profoundly space-time can be affected by gravity. But black holes are not the only cosmic phenomena that impact space-time. Dark matter and dark energy, two of the most mysterious substances in the universe, also interact with space-time in ways we don't yet fully understand. While dark matter doesn't emit or absorb light, making it invisible to telescopes, we know it exists because of its gravitational effects on galaxies and clusters of galaxies. Dark energy, on the other hand, is thought to be responsible for the accelerated expansion of the universe. Both dark matter and dark energy affect the distribution of mass and energy throughout the universe, and in doing so they alter the curvature of space-time itself. However, their exact role in shaping space-time remains a subject of intense study. As our understanding of space-time deepens, we also begin to explore the ways in which space-time is linked to quantum mechanics, the realm of the very small. The search for a unified theory of quantum gravity, which seeks to combine general relativity with quantum mechanics, is one of the most significant areas of research in theoretical physics. Concepts like string theory and loop quantum gravity propose that space-time is not continuous, as we once thought, but instead is made up of discrete chunks at the smallest scales. This suggests that space-time might have a more granular structure, one that could radically change our understanding of the universe. One of the key challenges of understanding space-time at the quantum level is that the curvature of space-time near singularities, like those found in black holes, is so extreme that it leads to what we call a quantum foam, a turbulent, chaotic region where quantum fluctuations occur on incredibly small scales. At this scale, the fabric of space-time itself seems to become fuzzy, challenging our ability to describe it with traditional methods. The idea that space-time may be made up of discrete elements opens up exciting possibilities for how we might manipulate or explore space-time in the future. If we can understand the granular structure of space-time, it could potentially lead to new technologies that allow us to manipulate gravity or even control the curvature of space-time in ways that seem science fiction today. Could we create artificial black holes? Could we warp space-time to travel vast distances quickly, similar to the ideas presented in warp drives and wormholes? Exploring space-time isn't just about understanding black holes and dark matter, it's about deepening our understanding of the universe itself. Space-time is the very fabric of reality, and every new discovery in physics seems to reveal more about how it works. Space-time doesn't just shape the motion of galaxies, it also shapes the evolution of the cosmos and the behavior of particles on the smallest scales. As we look toward the future, the study of space-time promises to reveal even more mysteries and insights about the nature of the universe, time, and the forces that govern both. In the coming years, as we continue to develop new tools and technologies for observing and experimenting with space-time, we may find that the connections between space and time are even more profound than we imagine. Whether through the study of black holes, the exploration of dark matter and dark energy, or the quest to understand quantum gravity, the interconnected realms of space and time offer one of the greatest frontiers in modern science, and as our understanding of space-time continues to evolve, we may just uncover some of the most profound truths about the universe and the very nature of reality itself. As we conclude our exploration of time, we've covered a vast array of ideas, from the fundamental concepts of time's directionality to the most cutting-edge theories in physics and philosophy. Time is not just something we experience every day, but a mystery that has fascinated scientists, philosophers, and thinkers for centuries. Throughout this journey, we've seen that time is not as simple as it seems. It's a concept that connects everything from our daily lives to the vast cosmos. We began by looking at the arrow of time, the idea that time moves in one direction, from past to present to future. This directionality is closely tied to the second law of thermodynamics, which tells us that entropy, or disorder, tends to increase over time. We've seen how this process plays out in everything from the evolution of life on Earth to the expansion of the universe. Yet, even as we observe this irreversible flow toward greater entropy, the very nature of time itself continues to elude us. We've also explored the fascinating relationship between time and space, particularly through the lens of Einstein's theory of relativity. Time and space are not separate entities, but are woven together into a unified fabric known as space-time. This discovery reshaped our understanding of the universe and showed us that time can be stretched, compressed, and even warped by gravity. Black holes, for example, are not just regions where gravity is extreme, they are places where time itself behaves in strange and counterintuitive ways. The closer you get to a black hole, the slower time moves relative to someone farther away. This warping of time raises profound questions about the nature of the universe, and whether time, as we understand it, is truly an immutable force or something more flexible and dynamic. In our exploration, we also touched on the psychological and philosophical aspects of time. How do we experience time in our minds? How does consciousness shape our perception of time? From altered states of consciousness, such as during sleep or meditation, to the scientific work of thinkers like Antonio Damasio, we've seen that our experience of time is not just a passive observation. Our brains actively construct our sense of time, linking the past, present, and future in ways that allow us to make sense of the world around us. Time, in this sense, is not just something that exists independently of us. It's something our minds create to navigate the flow of life. And yet, despite all the advances in understanding, time remains full of unresolved mysteries. We've discussed how time seems to flow smoothly in our everyday lives, but the deeper we look into the universe, whether it's at the quantum level, near black holes, or in the fabric of space-time itself, the more we realize how strange and complex time truly is. Quantum mechanics, relativity, and cosmology all offer competing visions of time's true nature, each one challenging our classical understanding of this fundamental concept. This brings us to a profound philosophical question. Could time be an illusion? If time can be bent, slowed, and even altered by consciousness or gravity, does that mean that the passage of time as we experience it is nothing more than a mental construct? Or is time an essential, immutable feature of the universe, woven into the very fabric of reality as space and matter are? These questions remain unresolved, and our journey through the nature of time has shown that there is still much to discover. In the future, we may gain deeper insights into the true nature of time. As technology advances and our understanding of physics and consciousness deepens, we might uncover new ways to manipulate time, or perhaps even experience it in ways that today seem beyond imagination. But for now, the paradoxes of time, its directionality, its connection to space, its role in consciousness, remain a captivating and open field of inquiry. Time is more than just the ticking of a clock. It shapes our lives, our universe, and even our perception of reality itself. And as we continue to explore time's mysteries, we may one day arrive at a deeper understanding of what time truly is and how it is connected to the very nature of existence. As you reflect on the ideas we've explored, think about this. Is time a real, fundamental feature of the universe, or is it just a byproduct of our perception, an illusion created by our minds to make sense of the world? The answer may be far beyond our current understanding, but that's what makes the study of time both scientifically and philosophically, so endlessly fascinating. The exploration of time is ongoing, and with every new discovery, we inch closer to understanding one of the greatest mysteries of existence.